Okay, welcome back to part 2. So we just saw this very scary bit of code. And it's a bit messy and ugly. But we're not going to get any worse than this. Okay, so it'll get better from now on in. Now, if we wanted to completely avoid having to write this kind of scary code, then really you would get somebody else to write it for us. But in a more general way, to provide a library of building blocks for building parsers. And that's what parser libraries do. And I may give you a bonus lecture next week, if you're good, which I might show you an example of how we could do that with this parsing job. But for now, all we're going to do is this brute force style parsing. We've got one problem to solve, parsing expressions, and we're going to solve it the best we can, but do not much more than that. But this is a good warm-up, parsing one of these things, because if we can parse this, then nothing in the main problem gets much more difficult than that. But what is the main problem? Well, it's parsing general arithmetic expressions. And in order to do that, we're going to have to understand that we can understand the structure of an arbitrary arithmetic expression by breaking it down into different sub-expressions. And we're going to give each of those sub-expressions names. Now this is standard, this is not, this terminology is standard mathematics, it's not specific to our Haskell programming. But when we have arithmetic expressions, then every arithmetic expression, like this one here, can be thought of as the sum of one or more things. And those things that we add together, they're called terms. Okay? When we talk about terms, we mean the pieces of a sum. Okay? So the terms are the pieces of a summation. So the terms of this expression are 1. This one here, 2 times 3 plus 4, that's the second term. And the third term is 5. Okay? But there may be no more than one term on its own. For example, that's a term on its own, and that would also be an expression. So what are terms? What are each one of these things? If an expression is a sum of terms, what is a term? Well, a term is a product, a multiplication. So when we say products, we mean a multiplication of one or more things. So this is the multiplication of one thing. Okay, that's why there's no multiplication sign. This is the multiplication of two things. This is the multiplication of one thing. So each of these is a multiplication of one or more things together. Each one of those things you multiply together, we're going to call that a factor. Okay? So a term is just a product of factors. And what is a factor? A factor is either just a number or it's an expression inside brackets. Okay? So whenever we look at an expression, we can break it down into its terms and its factors using this deconstruction. And why is that important? Well, it's important because that's the way that's going to allow us to take an expression as a string and convert it to an expression in our data type correctly. And what I mean by correctly is with the grouping in the right order. So if we have 1 plus 2 times 3, we've got to make sure that that's an add of 1 and a mul of 2 and 3. We've got to group the things together. So remember, the brackets are not something that's visible in the data type. The grouping of things is represented by the way we build expressions. Okay, so that's important. So grouping is not something we don't get for free. We have to build our expressions in the right way. And the way we're going to do it is to follow this way of thinking of expressions as terms added together, and a term as a factor multiplied together, and a factor is either an expression in brackets or a number. Okay, so let's start with expressions. An expression is going to be a bunch of terms added together. Okay? Now what I'm going to do is define 3 parsers, one for expressions, one for terms, and one for factors. But they're all going to be defined in terms of each other. So expressions will be defined using term will be defined using factor, and factor will be defined using expression. So this is called mutual recursion. It's recursion, but it's not direct. Expression is not going to use expression directly. It's going to do it indirectly through these other guys. Okay, so it's another form of recursion. Okay, all right. Let's have a go at this then. So this is going to get a bit sweaty, but we'll get there. Okay, so this is going to be expression is going to be a parser for expressions. So what is a parser for expressions? Well, it's a function from strings to maybe an expression and a string. So how am I going to parse something of this shape? Well, I've done something like that before, haven't I? Before the break, we looked at this guy here for parsing not terms, but numbers. So it's actually very similar to this thing. So if I copy that, that was a warm-up, and I paste it over here, it's almost the right thing. What do I need to change? Well, I don't want to parse num, I want to parse terms. I've got a function for that, it's over here. Okay, it's not finished yet, it'll be finished soon. So it's a term, and the first thing will be a term t. Okay, I don't need to change the name, but we'll do that anyway. Probably. And this is not an expression that we're going to parse, but, so it's not expression 1, it's going to be an expression. Okay? So that type checks. I can't do very much with it yet because term is not defined. Okay? But what was a term? Let's remind ourselves what a term was. It's one of these things here. Okay? A term is one or more factors multiplied together. So hey, we've done something really similar to that. We can just take this guy over here and all right. So let's suppose that I do that. I'm going to do it. I know it's wrong, but I'm going to do it. And then we'll fix it afterwards. Okay? So what do I do? What do I change? What do I need to change? We're doing factors, not terms. So I need to change that thing. That's number 1. Keep that in your head. Number 1, I'm changing terms to factors. Number 2, each of the factors is going to be separated by the star character, the multiplication character, not the plus character. So I need to change that one there and that one over there. And when we build the result we build will be built using not the add constructor, but the mul constructor, because we're building multiplications. And the recursive thing that we call is not going to be expression, but it's going to be term. Okay? See if that type checks. No. You see, that's what happens when you cut and paste. Always get something wrong. What did I do wrong there? Anybody see what I've done wrong? Something on the left-hand side here.
Term doesn't have any parameters.
Yeah, term doesn't have any parameters. Thank you very much. Okay. All right. So it type checks, but I did something very bad. You all saw it. I cut and paste. So what do we do to fix it? Well, we generalize. Well, that's one way. So there's, if you have two bits of similar code, there are a couple of different strategies, actually. One is, can you define one of them using the other one? So instead of copying the same code, can you define one in terms of the other? That's not going to work here. The other strategy is to build one piece of code which is more general than both of them, where the bits that are different between those two bits of code become the parameters. Okay? We saw examples of that earlier. We're going to do it again. We saw examples here in the lecture on higher order functions. That's where higher order functions come from. They're ways of generalizing patterns of computation. The things that you pick out that are different between the different uses are often functions. And that's going to be the case here as well. So the thing that's different, maybe just try and center this so we can see them both. The thing that's different between these two uses of this code, I'm going to build a more general thing for parsing a chain of things. Okay? So it's going to have at least one parameter, which is in common with this one, S, but it's going to have a bunch more that I'll add in a minute. And what are they? Well, we need one parameter for each of the things in these expressions which is different. How many things are different? Well, there were three things which were different. The first one was the parser that we use to parse the first thing. In this one we use the term parser. In this one we want to use a factor parser. So we're going to use some parser, we'll call it P. That's the first extra parameter. The second extra parameter is the character that we're going to recognize in between every one of these that we find. This one was the star, this one was the plus. In the general case, it'll be some character C. And the third thing was the thing we used to build the result. Here we built the result using mul, and here we used add. In general, you're going to use some function to build the result. So this is the only legitimate cut and paste that we're going to do, and that's where we generalize this, not to use term, but to use the parser P, not to use the expression here, but to use chain with P, C, and F, not to use add, but to use the function that we provide. Now, the only thing we need left to change is this character here. It shouldn't be the plus symbol, it should be C. Except I just made a mistake. That won't work. So why won't that work? Why couldn't I change plus to C?
Because now you're defining a new C instead of using the old one.
Very good. We're defining, we cannot pattern match on a variable. Okay? Because then we can't tell the difference between pattern matching on a variable and defining a new variable. So you cannot pattern match on a variable. Even though this is the guy I want to match, I can't pattern match on it. Okay? So this is some new character, C, and what I want to do instead is add a guard. So just like we use guards on recursive equations, we can also have guards in case expressions. And the guard is that the character C prime should be the same as C. And in that case, we carry on. Otherwise, we do whatever we had. So we found, so that needs to be C prime. Okay. All right, so now I can get rid of my ugly cut and paste. I'm going to cut that drastically. This is a chain of terms separated by the plus character, and where we build the result using the add constructor. Okay? Whereas terms are chains of factors, which we haven't yet defined, but we'll do that in a minute, separated by the multiplication symbol, where the result is built using the mul constructor. It type checks, a bit of surprise to be honest, but anyway. Let's just run lint on that, hlint on that, to see what other sins we've committed. So hlint, there it is. Okay, so it has spotted something that it didn't like very much. And this thing here. What it's saying is, this is what it found. And what it's saying is, why not this thing here? Okay? So this is an example of what's called eta reduction. If you take a function of many arguments and you remove an argument, then you get a function that's waiting for that argument. So this thing here should maybe give us an expression and a string. If I remove the s here, it becomes a function from strings to maybe strings and maybe expressions and a string. And so we can remove the s on both sides. It's saying this function is equal to this function. So whenever you use this guy here, if you apply this to a string s, it'll be the same as applying this to a string s. It'll give you the same thing. So that's what the advice is from hlint, and it's saying the same thing about this guy over here. We can define this function in terms of this function. Okay, and I don't think hlint has much more to complain about because we're not doing very much more in this file. Okay. Any questions? Okay, so that was a nice little exercise in generalization. Now the final case is a factor. I don't know why I've written them in this order because it was kind of awkward, but anyway. A factor is either an expression in brackets or a number. So this is, I can't use this chain pattern for this one. I have two possible cases. I either find a number or I find an expression in brackets. So I'm going to define this by pattern matching to distinguish these two cases. The first case is where it starts with the open bracket symbol. In that case, that's when I'm going to look for an expression and a closed bracket symbol. The other case is where we have some string which doesn't start with an open bracket. So if it doesn't start with an open bracket, then it must be a number. I've got a parser for one of those I wrote earlier. It was called num. Okay, so I've only got one more case to crack, and that's this one here. So what am I going to do? I found an open bracket. Now I'm going to try and find an expression. What parser do I use for that? The expression parser. But then my job is not done when I find an expression, because after I find an expression, I've got to find the closing bracket. If you have an open bracket and an expression, you've got to have a closed bracket, otherwise there's a syntax error. Otherwise I'm going to return nothing. So I need to do a case expression. If I'm successful, then what will it look like? If I'm successful then, I'll do it on the same line here, I will find just of some expression and the next symbol in the string after the expression will be a closed bracket symbol. And if that's the case, then I'm happy. I return just the expression and the rest. But if I get anything else, for example, an expression followed by something which is not a closed bracket, then there's something wrong. I'm not going to be able to recover from... Once you've got an open bracket, you're committed. There's got to be an expression and a closed bracket. Anything else is junk. So if I get anything else, then I'm afraid I have to return nothing. So that's the parser for factors. So let's take a simple example. Can I get a factor from 1 plus 2? Well, I can get the 1. Could I get the factor if I put brackets around the 1? Yes, it would give me the same thing. But if I start with a bracket and don't end with a bracket, then I get nothing. But now everything is defined. In fact, now I should be able to parse everything. So what do you expect me to get when I parse the following expression? I'll remove the spaces because I haven't taken into account spaces. I'll do that in a minute. So what do you expect to get there? So spend a few seconds jotting down what you think the result of this parse will be. Okay. So how many people you think you get nothing? A few. So the rest of you then think you get just of something. So if you get just of something, how many people think you get just of an add of something? How many think you get just of, brackets, a mul of something? Let's have a look. It's just of an add of something. And what is it the add of? It's 1 added to the multiplication of 2 and 3. And what about this divide operation? Well, that wasn't something we know how to parse. That's not part of our data type. So that's just some of the junk on the end. That's what you get after we've managed to parse an expression. So we managed to parse an expression, but then we ended up with something that we don't know how to parse. Okay. What about this case? 1 plus pi. Well, you managed to successfully parse the 1, but the plus pi is part of the junk. Okay? We can't build an expression from that. The biggest expression we can build is the 1, starting at the beginning. Okay, so I'm trying out a few examples here, but I think it's very useful to, well, there's one more thing we should do. So this extra stuff on the end, what is the point of that? Well, the point of that is in order to be able to combine parsers for smaller things to build parsers for bigger things. That's why we keep the rest of the string. Because, for example, when we're parsing an expression, we might start by parsing a number, and then we need to use other parsers to parse the rest of the string. So that's why we keep the rest of the string. But when we've built the parser we're interested in, and that's this one here in actual fact, then when we use it, we actually don't want any rubbish on the end. We don't want things like this. So what we're going to do is define what we call a top-level parser, which has a slightly different, slightly simpler shape. I'm going to call it read expression. And what it's going to do is take a string and maybe give us an expression. Okay? So, and what does it do? Well, it's going to take care of two separate things. It's going to throw away any spaces that we have in the expression, because at the moment, if I write expressions with spaces in, they're not going to work. So that wasn't a good example. They're not going to work as we expect. If I put a space in the front, then, oh, that's cool. Oh yes, of course. Spaces in the front are fine because the parser for numbers doesn't care about spaces in front of numbers. But this space causes us problems, the second space after the number. So we need to get rid of those spaces, and we need to check that there's no junk at the end of the string. Okay? So what we're going to do is we're going to apply the expression parser to the string and check out the result. Was there a question? No. So if I get just an expression together with the empty string, no junk, then everything's cool. I can return just the expression. Otherwise, I can return nothing. That looks a bit odd. Oh yeah. Okay, I took care of no junk. So this is saying I don't expect to see any junk after I've found an expression. But I forgot about the getting rid of the spaces. So let's get rid of the spaces. So how can we do that? Well, we could take the string and we could throw away all the space characters. That's one way of doing it. So we're going to use that way. It's very simple. It'll do the job. So what I'm going to do, I'm going to filter all the things which are not spaces. So I'm going to use the filter function for that. And I'm going to feed the filter function with not composed with is space. So I'm building a little function that tells me when something is not a space character by composing using function composition, the isSpace function from data.char and the not function. Okay, so now I should be able to parse any old expressions. Let me just reload that. I'm not sure I managed that. No, that didn't work. Oh, that's because I'm using the wrong parser. The read expression parser, and it doesn't matter how many spaces I put in or how many brackets, as long as it's a well-formed expression, there'll be no problem in parsing it. Of course, if I leave out a bracket, then that's a bit of junk. So now I have an expression parser that maybe gives me an expression. It gives me nothing when it fails and gives me just of an expression when it succeeds. Any questions? Okay, in the last 10 minutes or so, I want to talk a little bit about testing. I don't know what happened here. I got mad with my typing. Okay, so in order to talk about testing, we're going to take some of the old functions that we defined before. Eval, that could be useful, but perhaps more importantly, showing, because parsing and showing are somehow related, right? And in order to run quick check, if we're going to do quick check stuff, we'll need the stuff we defined in the lecture for arbitrary expressions. So that was the code that I'm taking directly from that lecture. So one of the properties that we expect is a relationship between show and read. Because read, or at least read expression, converts strings into maybe expressions, and show converts expressions into strings. So they're kind of almost inverses of each other, maybe. In the sense that if we start with an expression and we show it, we get something like that. And if we then take that and we read it, using then what do we get back? Well, do we get back this thing? Almost. We get back just of that thing. Okay? Because the types don't quite match. So if we start with something, we show it, convert it to a string, then we know that that string must represent an arithmetic expression. It shouldn't have any junk in. Shouldn't have any nonsense. So that when we apply this function, it should succeed in reconstructing the expression we started with. Right? That's the idea for a test. So let's try it out. If we show the expression, and then the result of that, we apply the function read exp, then what we should get back is not the expression, but just of the expression. Okay? Maybe not. Exp, oh, yeah, can't decide what to call my parameter. Okay, well, let's try it. Let's quick check it. Oh, that didn't work so well, did it? What did I do wrong there? If I show that thing, I actually don't know what's wrong with that. It's such a small example, how could it possibly be wrong? I have absolutely no idea. It looks all right. If we take that, if we read exp, the thing we got from the previous line, oh, something wrong in read exp.
You're not using the right show function.
Ah, I'm not using the right show function. The problem is that there is two ways of defining show. One is to use show exp, which is the one I want, and one is to use the built-in show, the standard deriving show. And I commented out the show exp version, and I'm using deriving show. So of course it's not the show function I want to use at the moment, it's show exp, the nice show function. Thank you. Now it should make more sense. Now it should work, right? Well, not quite, but that's kind of what I expected. These things don't quite match up. But do they match? Do they fail to match up in an important way? I'm just checking how much time I've got left. Okay, I've only got 9 minutes left. So one of the problems we have here is that quick check, the counterexample for quick check gives us is really big and complicated. Now that can be improved by helping quick check in building smaller counterexamples. But to do that, we do need to do something we didn't look at when we did quick check, and that is a function called shrink. So shrink is a quick check function which you don't have to define. It will be defined automatically, but not very well. But what it does is whenever quick check finds a counterexample, it calls a function called shrink to try and find smaller counterexamples. So when it finds something that makes your program go wrong, it tries to find a smaller example using shrink. And what shrink does is, for anything that you can do quick check on, it takes the thing that it found and gives a list of suggestions for smaller things, which quick check will use to see if it can find a smaller example. And unfortunately, we didn't define the shrink function for our data type. So our counterexamples are big and ugly. But I think I know what the problem is, because I've given this lecture about 4 or 5 times, so you know. So the problem is there's information loss. When we read an expression, for example, 1 plus 2 plus 3, you see it's an add of the number 1 together with the add of a number 2 and 3. Now, if I provide a slightly different expression, which is that one, it will give me a different expression. Agreed? And why is it? Because it's grouped them in a different way. But we don't really care about how plus is a group because it's an associative operator. So we haven't bothered to think about that. So what is the result? Well, the result is that when we show, using show exp, this guy, oh, I should have left the brackets in. When we show the first guy, we get that. When we show the second guy, which is that one there, we get the same thing. So what's happened is that even though the thing group, when the adds are all grouped to the left, when we show it, they all get moved over to the right. So all we're doing is rearranging nested additions. So what we need to do is not check whether they're exactly the same, but they're the same if we rearrange all the associative operators in this guy. So to do that, we need a function. We need to define a function for that. You could call it a soc. And what it will do is, whenever you have something of this shape, with an arbitrary expression E1 and E2 applied to an E3, it's going to rearrange that to be add of E1 and add E2, E3. And it's going to do the same thing with null, and I'm cutting and pasting again. And the one to blame is the data type definition, not the author. The data type definition forces us to do cut and paste because we can't pattern match on null and add because they're functions. So we need to do that, rearranging, but we not only need to do it once, but we need to do it as many times as necessary until there are no more adds inside here and no more mulls inside here. So we need to recursively associate again. Each time, the left-hand argument will get smaller until eventually we'll be associating a value of the form mul E1, E2. And I'm aware that the time is running short. Associate also with add, where these things are not nested anymore. And then all we have to do is recursively go inside and reorder those as well. So we need to take these guys and recursively reassociate the smaller parts because we might have more of these things inside.
Why do you even have to do that?
Well, because the show function will go down inside and we'll do the same. This thing we saw in the example, that could happen deep down inside an expression. So we better make sure that we do the assoc. When we reshuffle, we also go deep down inside the expression. And the only way we have of doing that is by using recursion. So now what we're saying is that if we reassociate this so everything is shifted over to the right, then it should work. Time's running out. You better work. No. I forgot one of the cases. Almost there. A soc for a num n. We can't do anything with a num, but we have to remember it's there. One more quick check. And we're done. Awesome. Thank you very much.